Okay, so we're going to start this problem over again. And a car moving with initial velocity 5 miles per hour, okay, accelerates at the rate of 2.4 t miles per hour per second. Okay, and that's accelerating for 8 seconds. So we want to find out how fast is the car going when the 8 seconds are up. And then part B, how far did the car travel? So how far something traveled, that's going to be the integral of velocity. Kind of a train problem that we talked about at the very beginning of chapter 5. And then we revisit it a couple times. So for part A, oops. So for part A, we want the net velocity change, basically, which is going to be the integral from 0 to 8 of a of t dt. Okay? Does that make sense?
Why
Like it's the total change.
Why are we using change as well?
Well, it starts out at 5. We can add in. Here. Okay. It's kind of like displacement. So remember when we did the particle movement and we had the final position was the initial position plus displacement? This is kind of like that. So we're going to add in the initial position, or in this case, initial velocity, and add that to the total change.
So it's like calculating 0 to 60, but you have instead of 2. So basically think how much it accelerates and absolutely not.
Right, so this is just going to give us how much the velocity increased over the 8 seconds, and then we'll add in the initial velocity. Does that make sense? This is like, I'll put it in here. It's like displacement. Oops. Okay, so let's figure out what that's equal to. So 0 to 8 of 2.4 t dt. What do we get for that? Over 2. So that ends up being 1.2 t squared evaluated from 0 to 8. Does that, right? 2.4 t squared over 2. And so what do we have? 70, anybody have a calculator? 76.8. And this will be miles per hour. Because remember how the acceleration was described? It was miles per hour per second. So when we integrate using seconds, it eliminates the seconds.
Add 5 though?
Right, so we're not done with this problem. This is only the change in velocity over the 8 seconds. So we want to add in the initial. Okay, so since v of 0 equals 5, when the 8 seconds are up, it's going to be 5 plus 76.8, which we get 81.8 miles per hour. Right, the final answer for part A is 81.8.
And here's the problem in the work, you say like this, but it doesn't say like the v of 0 equals 5.
Does it say that does it say maybe initial velocity is 0? Does it say it in words?
It's starting from a complete stop.
Okay, maybe it says something like that. We'll look at it. What, you don't remember? You don't memorize all the problems from homework?
We're not in this case.
I don't memorize all the problems from homework.
You should.
I should. You're right. A good teacher would do that. Okay.
I didn't mean it.
It's okay. It's all right.
I didn't mean it that way.
Okay. How far did the car travel during those 8 seconds? So what is that going to be?
The
Displacement.
And
That's,
Integral velocity.
now, displacement is, notice I said here, like displacement. It's not, I meant that it was the net change in something. But now when we actually do displacement, we're gonna do the velocity.
The integral of velocity.
Right, so this is gonna be, sorry, I didn't leave a lot of room here. It's gonna be from 0 to 8 of velocity. Or actually, I'm sorry, I don't wanna put the bounds in right now. Because I don't have, I'll explain. It's basically because I wanna come up with the velocity function, which involves the initial. Now, some of you may be able to see it now, but let me just go through the steps. Yeah, Natalie.
So, we do not have to do
That's
Oh.
exactly what we're gonna do. So C really ends up being 5 in this case. So it's not always the case, but that's why I wanted to take it step by step. I didn't want to put in the bounds just yet. Yeah.
But then why in like the definition of a displacement like there's bounds in it, but in some cases you don't need bounds, so you don't need.
Oh, so we didn't actually find the velocity function. If we found the velocity function, then we would put bounds in from 0 to 8. Okay. Let me explain.
They gave us what?
We only have acceleration at this point. We found out the total change in velocity, but we didn't actually figure out the velocity function. Once we figure out the velocity function, then we can put in from 0 to 8. Does that make sense? So I technically can put in 0 to 8 right here, but this is V of t. This is what we need to find. Now, we kind of did all the work already, so this should be relatively easy when we put it together. Let me just show. So, I know what I was writing yesterday. I wrote up the dsdt. Right? Do you remember, like, the second derivative? If you had a problem on that, like the test, you don't remember. Okay. It's fine. I'll just write it out this way. Oops.
He says it's look like.
But I didn't hand them back. I don't know. Okay. So let's find the velocity. Well, we already integrated it here. We said it was 1.t squared, but we're going to put plus c.
So why is C5 though?
So since v of 0 is equal to 5, when I plug in 0 for t, right,
Oh.
I get 5. Right, so apply this initial condition here, and we get c is 5. So v of t,
Integral of V of t, or we're finding V of t?
we're finding v of t.
Oh.
Okay, it's a little complicated because we have the acceleration function, but we don't have the velocity function. We can find the velocity function based on the acceleration and our initial condition. Okay, we did this in the last chapter, right? When we had to find a particular solution, right? I would give you a differential equation. We moved over the dx, and then we would integrate both sides, and then we get a plus c, and then we plug in our information, and we figure out what c was, and we go back and we solve for y. It's the same thing. It's the same thing. It's just now it's because it's an application, it's a kind of a word problem that we have to understand that that's what we're doing. Okay, we're not done. We're like completely out of space, but I have to remember to leave more space next year. So now we want to do from 0 to 8.
You know you can select all the times.
Sure. Thank you for that. But then you wouldn't be able to see it.
Why don't you just get a bigger
That's not the problem.
Okay, so now we want to integrate this. If you want, you can do this on your calculator, that's fine. I know that you guys can do this. So.
Wait, no. So now I'm just plugging in.
You guys did well enough on the last test that you've chosen it. So just plug this in. You could integrate this by hand. It would be 1.2 t to the third over 3 plus 5t evaluated from 0 to 8.
Got it. 244.8. 244.8.
244.8.
But doing it by hand was after that.
Why, right, but why waste the time if you have a calculator?
Because I actually did it all the
Okay, now let's talk about units for a minute. This was
Miles.
okay. Did it go 244.8 miles?
Oh.
No, it did not go 244.8 miles in 8 seconds. So when we integrated here, this was with respect to seconds, but we were working with miles.
So it
we
went
have to divide it by
244.8 miles per second.
Okay, so
That was not,
divided by
unless you're a rocket.
okay, so if we're working with seconds, so you guys have a
Oh, no,
problem like this on a
Unless you're
quiz.
light.
Wait, 3,000 was 200, right?
So remember, we did a problem like this on the quiz where we had to do the trapezoidal approximation. It was like a sled or something, and you had miles per hour, but I gave you the time intervals in seconds. So when we figured out that,
Divide by 3 on 2,600.
right, how many seconds are in an hour?
I'm talking about 0.068 miles.
3,600.
0.068 miles. If I did it right. 0.068.
Okay, so divide that by 3,600.
How do we know that's oh, because it says second.
Right, so go back here. Remember, we had different units. This was given in miles per hour, but it was per second, and it was over the 8 seconds. So when we have to think about our answer, does this make sense? Does 244.8 miles make sense? No.
Sometimes we're talking about a rocket or a particle.
This far.
But
Right, if we're talking about a particle, that could make sense.
But it says
it
far.
could. But because I know my bounds were in terms of seconds, not... Now, what if you wanted to change 8 and 0 in terms of hours? Could you have done that?
Yeah, but it's a lot more.
It would be 8 over 3,600. How many seconds are in an hour? Okay, so take that answer, 244.8. Oops. Yeah. Okay, so we get 0.068. Nope. So that would be miles, or if you wanted to change it to feet. No, I just want you to be familiar with it, because if you had a problem like this on a multiple choice problem, they could possibly give you your multiple choice answers in feet.
You just multiply it by what? 5?
Okay, so how many feet are in a mile? 5,280? Okay, so,
I didn't know that.
oh, yeah, I did it on my computer. But-
Yeah, I was more surprised that you remember the conversion. Like, yeah, I know.
Okay, let's move on. Unless you guys have questions on that.
I didn't know.
Be careful. You're right, it can be wrote outside the screen.
I know, but you need to take it.
Thank you.
Well, you put it in.
Ready?
Oh, no, that's not.
This is a calculator problem.
We were trying to figure out what the 244.8 is. Like, after, oh, the 244.8. Miles over what, though? It's nothing, you just have to
right.
convert it.
You have to convert it in order for it to make
Makes sense.
sense.
You know,
Because you were
figure it per
integrating
second.
and you were using, okay, so remember when we did U substitution and you changed your bounds? So this is kind of like we didn't change our bounds. We had seconds, but when we did the integral, that was miles per hour. So we didn't, if you wanted to change the bounds to reflect that, you would divide the lower and the upper bound by 3,600 to represent in terms of hours. We'll do some more examples of that. All right, let's do this one though. I want to get through all the examples that we have. This one is a calculator problem, so I just want you to be able to interpret. So another particle motion. Describe the motion of the particle. So in other words, when is it going to the right, when is it moving to the left, and when is it stopped? This, what is drawn here, is the velocity. Okay, so when the velocity is below the x-axis, then we know it's moving left. And then as soon as it goes above the x-axis, moving to the right. And when it crosses, not just touches, but it actually has to cross, then that's when it's 0. So let's figure out the x-intercept. So this is a calculator problem where you have to just type it in. Find the 0. Okay, so I have x squared minus 8 over x plus 1 squared. And I'm just looking at from 0 to 5. So if you wanted to change your window, you could. You don't need it. I'm just saying, if you wanted to, you could change the window to what's here. But it's not necessary. So let's find the 0. And we get 1.255?
Yeah.
Okay, so that's, I got 1.255. That's, remember 3 decimals, always round to 3 decimals, please. Okay, so when is it? This is really easy, guys. We just want to basically write this out. So it's moving right. Okay, so it's moving left. When? From
0 to 1.255.
Okay, so from 0 to 1.255, and then moving right, 1.255 to 5, and it stopped at t equals 1.255. That's all. I mean, this wasn't a difficult problem. It was just reading, what you were given and interpreting.
That's why it's AP level.
This is AP level. This could be an AP question.
They would actually.
Yeah, they would. It would be a multiple choice problem, but yeah. They might say, they might give you a problem like that, and then they would say, when is the particle moving to the right? So you'd have to go in and find the x-intercept, and then just interpret that from the graph.
How do they enforce no calculator problems in the test?
Because you take it apart, yeah, so they've got you. Okay. Example 5. So.
You know that?
Yes, I know. They told me I can't just use them on my surface.
I'll make you think.
Suppose the initial position of the particle in the last example is 9. Okay, so what is the particle's position at 1 second, 5 seconds? Okay, so 1 second is, well, it's still moving left, right? And then the 5 seconds is when it's done. So we're basically taking this last example. It's still a calculator problem. You're going to do this all on your calculator. I guess you could do it by hand, but again, you guys, we've done this, so the first part is basically referring to the new position, or you can think of this as final position, whatever. You can figure out the position anywhere on the interval as long as you have the information, like you have the function and you have it a value at some point. It's the one above. Example four. So what's displacement? Let's figure out displacement first.
I have a very confused definition of
Okay. Moving along. 0 to 1. What was it? T squared minus 8 over t plus 1 squared dt. Yeah, so I want to just do the displacement for this. If you wanted to, you could do you could solve this by hand. Oh, because the first one is 1 second, and then we'll do 8 seconds. Or, sorry, 5 seconds. I'll just, you know what? I'll just write it out just so you have it. So t to the third over 3, plus 8 over t plus 1. And we want to evaluate this from 0 to 1. Sorry. Yeah, just to save time.
Wait,
Did I forget a subtraction sign? Oh. That's what I did. That was good. It was right. Oh my. But the answer is negative 11. That is correct.
Oh, we don't have that tonight.
So we plug this in. That's just the displacement. Now we'll add in the number. So the displacement over the first second is negative 11/3. Now to find the position. But then plug in 0, and then we get a minus 2. You'll be subtracting 8. So the position at t equals 1.
How is subtracting even if you plug in 0 and there's no negative?
That's minus 8.
Where are we subtracting?
Subtract 0.
So you're minus
2.
Oh,
Do you want me to
what-
write out the word? I can write it out if you. Are we having trouble seeing why?
What's the number?
Just literally plug it in and you'll see what happens.
1/3, but we're integrating 1/3
I'll do
plus
it.
8.
No,
Here.
but then you're subtracting the eight.
Okay.
Oh, right,
Just
minus. Oh, did I leave out more? Oh, right, there we go.
Now.
Oh, right. It's when you I forgot that when you plug in a 0, you're not getting a 0. That was,
Yeah, because there's a 0.
right.
Makes it
That
easier.
makes, now that makes sense.
Now it makes
Yeah.
sense. All right, how about the next one? Yeah, the displacement. So it's asking whenever you're looking for like your final position or position after a certain amount of time, we're going to start at 0. Now, if I ask you for how far did something travel from 3 to 5 seconds, then you would use 3 to 5. But we're looking at the whole from the beginning to a certain end second. Okay, so you would get 35, yay. So now our position at t equals 5 will be 35 plus 9, so 44. I know, this is long.
So we talking about one thing?
No, I mean like
Oh, like even this second part, so you're saying it should have been 3 days?
yeah.
I don't think I wanna do it 3 days.
It's not bad, it's just a lot.
We know how to do it.
And this part's easy. This is like the easiest of, I mean, it's one of those problems, like this is a calculator problem. Okay? I guess you could do it, no, this would be a calculator problem because it's put the 1.1 to the t. So, total consumption over time. Okay, total consumption over time. So the integral is a way that we can calculate net change. Okay, or total accumulation of more quantities other than just like distance and velocity. So it can be used to calculate growth, decay, or consumption. And the cumulative effect, so it's like basically adding it all up, right, of any varying rate of change. That's what we're going to do. We're going to integrate it. So when we want to find, for example, in this next example, the rate of potato consumption. I took the problem from the book, so. Okay, so from 1970 to 1980, the rate.
Say it's in Latvia, then the answer will be zero.
Okay, if it says particular country, I don't know what country. Don't ask me what country. And don't ask me bushels. The class last year looked it up. I don't care. Okay. C of T. So C of T is a rate. So whenever we're looking for total consumption, what we said here is the total consumption is going to be equal to the integral of the rate at which something is changing or purchasing. Right, and this is usually with respect to time. Not always, as an example. So from 1970 to 1980, we know that this was the rate of potato consumption, with T being in years since the beginning of 1970. So how many bushels were consumed from the beginning of 1972 to the end of 1973? This is all about just interpreting the bounds. Okay, so let's set this up. So our total consumption okay. So we know it's going to be this. We want to figure out the lower bound and the upper bound. So the beginning of 1972 means our lower bound's going to be 2. And then the upper bound, now it says end of 1973. This would correspond to the beginning of 1974. That's just a way to interpret that. So it's actually going to be 4. I know. So that's why I wanted to show you the actual problem itself. It's not that hard. It's just interpreting how to plug in the bounds. That's really what this is testing you on. So just pay attention to the wording. If it said beginning and beginning, then it would be 2 to 3. Or if it said end, it would be 3 to 4. Okay, if it doesn't say anything, then we assume it's 2 to 3. What do we get? 7.066 million bushels. Yeah. into your calculator.
So obviously lot the other is done. It's
Yes, it is a real unit of measure. I don't know what it is. Okay. Graph of the velocity is given. So when the particle starts at x equals 2, when t equals 0. That means that's the initial position. That's s of, what this means here is s of 0 equals 2. Or you can say x if you prefer. X of 0. Whatever you want to call your position. This is I probably should have labeled it, but this is V and this is T. This is V and this is T. So, right, if you have velocity and you're looking for where the particle is at the end of the trip, you're talking about what? Wait, what are we looking for? Where's the particle at the end of the trip? That's final position. So it's the initial position plus the displacement. Got it? So for part A, we went final position. Let me just write that out so you have it. So it's going to be the initial position plus displacement. So the initial position we already said was 2, plus the displacement. So from 0 to 10 of v of t dt. Okay, well what is the integral? It's, okay, so we have a trapezoid and the triangle is going to get subtracted. Or you can divide it into rectangles and triangles. It's how you want to divide that up. Go ahead. You want to make it into a trapezoid? Oh, that's the initial position plus the displacement. Good. Yeah, what's good?
Yeah, exactly.
It's a small bit to make it. Okay. Okay, did we get it yet? 2 plus. Yeah, this area is 1/2. I'll just make it into a 2, and then 6 plus 3. So I got 9 for the trapezoid, and then here, this area is just going to be 1/2 4 times 2, so we get 4. And that gets subtracted though because it went below the x-axis. So we get 7. Okay, find the total distance traveled. So what's the total distance traveled? So that means any places where the velocity was negative, which is from 6 to 10. We just want to count that as a positive. Right, but okay, the question is, total distance traveled, so do we care where it started? No. So we're just going to basically add this area and this area.
To the 2 or not?
Not the 2. So there's total distance traveled is just going to be from 0 to 10 of the absolute value of v of t. Yeah, just 9 plus 4. No. So we don't need the initial position. We don't care where it started from. Yeah, we did put 2 in. It's the initial plus the displacement plus that. Okay, last one. Okay. A pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. So the rate, in gallons per minute, at which the pump operates is recorded at 10-minute intervals. For 1 hour. How many gallons were pumped during that hour? They give you a hint that you want to use subtotal. Yes. Yes.
It's H over two.
Okay, H over 2.
First Y and then H times Y. Then goes to the Y and to the Y.
Oh, but we have the heights are the same the whole time, so we figure it out.
Yeah, we'll have to do that, right?
Here, I'll write it out this way. So it's going to be H over 2. We'll have the initial rate plus 2 times rate 1 plus 2 times rate 2 and so on until we get to the last one, whatever that might be. And that's when we use them. So all the ones in the middle are going to use twice. The ones on the ends get used once.
I don't have to do that one because we're not the same.
No, okay, we don't have to do separate trapezoids
Oh, so that is
because remember you always want to check to see if the time interval is evenly divided, right? So it's always 10 seconds. So that's my H, right? So 10 over 2, and then it's going to be what, 58 plus 2 times 65 plus 2 times 58 and so on. And what?
I got 750 and you got
Yep. And double check to make sure did any units change. Just be careful, like this was in minutes and this was gallon per minute. So when we take the integral, we are just left with gallons. So you just want to pay attention because sometimes if they give you the rate is gallons per second, then you have to take that into consideration.
When do you divide that number by another number? Because then sometimes you have to.
That's what I was just saying. So since here, since those two are the same, so when you have a rate and the rate is based on the same time increments that were provided, then you don't need to do anything. But if you had, okay, so what would this look like? What would this look like if this was given in gallons per second?
You would have to multiply by 6.
You would have to multiply by 6. Because if you, yeah, because this would be gallons per second. Or what if this was gallons per minute and this was in seconds? Then you would divide by 60. Do you see that?
Because you always want to get what that is.
Right.
Which one do you want to get?
Okay, so I wanted to show you like there are two different ways to look at it. If this was seconds, but this was minutes, then you would take your answer and you would. So if this is seconds, what would you do? That you would divide by 60. But if this one was seconds and this was minutes, then you would multiply.
Time again, whatever. It'll be less of it.